So the binomial formula states that if n is a natural number and x and y are complex numbers, then if you raise x plus y to the power n, then you can expand this product as a sum of n plus 1 terms, and each of them is of this form n choose k times x to the k times y to the n minus k. Now, let's give a quick proof of this result. So note that when you expand x plus y to the power n, you write x plus y times x plus y times x plus y. And so here, we're going to have n factors. In order to calculate this, the outcome of this product, we have to pick from each bracket or from each factor a x or a y and make the multiplication and put them all together. Now we can pick, let's say we fix a number of x's that we're going to pick from these n brackets. Well, let's say pick k x's from these n factors. So if we pick x from exactly k brackets, their contribution is going to be x times x times x k times, so it's going to be x to the power k. Now from the remaining n minus k brackets, we're going to have y, so the contribution is going to be y times n minus k. And now how many times does a term of this form appear in this expansion? Well, it's the same number as the number of ways of picking k brackets from a set of n brackets. And by its definition, that number is n choose k. Now, what are the possible values of k? Well, k can be as small as 0, in which case we do not pick x from any brackets, and we pick y from all of them. So this summation is going to be take k from 0, and you can take any integer value from 0 all the way up to n, in which case we pick x from every bracket and we don't pick y at all. So that's the formula. Now, the other formula where we switch x and y can be proved very similarly, so I'm not going to go into details. Now, I want you to note that there is a formula, a more general formula that is due to Newton, in which this condition that n is a natural number is replaced by the fact that the exponent can be any real or actually can be even a complex number. But in our case, let's just say that alpha is a real number. And now if we have x and y, let's say complex numbers, then x plus y to the alpha also has an expansion, but this expansion is as an infinite series. So it's going to be of the form summation of k equals 0 to infinity of alpha choose k, x to the k, y to the power alpha minus k. Now you cannot do the same proof as before by picking brackets and all that. There are two realms in which you can deal with this formula. One is the realm of infinite series, where you have the notion of convergence and so on, and we're going to put that aside and do not worry about it for now. And the other one is in the realm of formal power series, and we'll discuss Newton's formula when we get to that in a lecture or so. Now, for this formula, x plus y to the alpha, probably it's pretty clear to all of you. X to the k, y to the alpha minus k, it's also clear. Alpha choose k, well, this has a definition, even if alpha is not necessarily is not a natural number or a non-negative integer, and is defined, alpha choose k is defined as alpha times alpha minus 1 times alpha minus k plus 1 divided by k factorial. So we'll come back to Newton's formula in a little bit. Okay. Now let's see some consequences of the binomial formula. So one of the easiest one is to show that the sum of all the binomial coefficients in n choose k is 2 to the n. Now you can give two proofs of this fact. So first proof is you look at the binomial formula, which is x plus y to the power n equals the sum of k equals 0 to n of n choose k, x to the k, y to the n minus k. And this is true for any x and y complex numbers. So just take x and y equal to 1, and then 1 gets on the left-hand side 2 to the n, and on the right-hand side you get the other expression, summation of k from n choose k from k equals 0 to n. Obviously, you can give a second proof, which is perhaps easier in this case, is the fact that 2 to the n is the number of subsets of a set with n elements, let's say the set of all numbers from 1 to n, and the subsets from of a set with n elements, you can sort them according to their cardinality, and turns out that the sum from k equals 0 to n of n choose k is also the same thing, is the number of subsets of n. Okay, so that's a result that you should know. There's something similar where we can prove that summation from k equals 0 to n of minus 1 to the k n choose k equals 0. Now, you've seen now the one example of plugging things into the binomial formula. So proof. Again, we'll do two proof. First proof is, again, you start with the binomial formula, x plus y to the n, summation from k equals 0 to n choose k, x to the k, y to the n minus k. And now you can take x equals minus 1 and y equals 1. And then on the left-hand side, we're going to get 0. And on the right-hand side, we're going to get summation from k equals 0 to n of n choose k minus 1 to the k, 1 to the power n minus k, which is exactly what we want. Summation from k equals 0 to n of n choose k minus 1 to the k. Now, this is one proof. Another proof can be given in the following way. What exactly is the left-hand side? So if you expand it, what type of expression do we get? So the left-hand side of this sum, summation of k equals 0 to n minus 1 to the k and choose k, something of the form n choose 0 minus n choose 1 plus n choose 2 minus n choose 3 plus and so on. Now, let's move to the next page. So let's rewrite this again. Summation from k equals 0 to n choose k minus 1 to the k, n choose 0 minus n choose 1 plus n choose 2 minus n choose 3, and so on. If you keep the terms with positive coefficients in one side, it's going to be the following. So let's just put it like this: n choose 0 plus n choose 2 plus n choose 4, and so on. And then on the other side, with the minus, we're going to have minus. Let's put a different color. N choose 1 plus n choose 3 plus n choose 5, and so on. Now, if you are a bit careful, you can notice that on this side, all the elements at the bottom are even. So essentially, what is this counting? This is the number of subsets. Let's call them even, the number of even subsets of a set with n elements, even cardinality. And here we have that this is the number of odd subsets of the set from 1 to n. So our result essentially, so what we're trying to prove is the same as showing that the number of even subsets equals the number of odd subsets equals, the number or odd subsets of the set n. Now I give you a hint of how to prove this fact. Let's say we do a proof by a direct proof. So let's say we have here E is the collection of even subsets. Let's say En, collection of even subsets. And let's say fancy O of N, it's the same thing, the collection of odd subsets. Now let's do a proof by cases. Case 1, N is odd. And I want to show that, so again, what I want to show is that, what we want to prove is that the cardinality of E of N is the same as the cardinality of O of N. And I'm going to do this by constructing a bijective function between these two sets. And this bijective function is pretty easy to do when N is odd, as you'll see in a second. So we construct this function. If I take, let's say E is an even subset, I map it to its complement, so it's N minus E. And the key thing here is that this function is well defined, and this is because N is odd. So because N is odd, the cardinality of this of the complement of an even set is odd. So this is an odd subset. So this is a legit function, and it's not too hard to prove that F is a bijection. So I leave that as an exercise for you to do. And because F is a bijection, that implies our desired result. Now you cannot use the same trick when N. So you have to deal with the second case, case 2, and case 2. Let me squeeze it here. Case 2 is N even. So I leave it as an exercise for you to figure out a bijection between the even subsets and the odd subsets of a set with n elements when N is even. It's not going to be as simple as taking the complement, but it's not difficult, and I think it's a good exercise for you guys to try. Okay. All right. So what other applications can we make from the binomial formula? So let me see what I have here. I did 2. Let's say 3. Well, another way you can create some or prove some binomial identities is look at this. You look at this binomial formula in a different way. So let's say let's write it for, just replace y by 1, and I have x plus y 1 to the n is this expression, because I took y to be 1. Now let's make this into a function. So let's create a function. For now, let's just say the function is from real numbers to real numbers, the different f from before. F of x equals x plus 1 to the power n. Now this function is obviously differentiable, and so f prime of x equals, by the rules of taking derivatives, this expression. But at the same time, you can take the derivative using the summation on the right. So that's going to be the derivative of the summation from k equals 0 to n of n choose k x to the k. And if you do the calculation, this is going to be a sum. It's actually from k, well, let's write it like this, k equals 0 to n of n choose k, k times x to the k minus 1. Okay, so the derivative has to be only 1, so, and therefore what you get is that n times x plus 1 to the n minus 1 equals the summation from k equals 0 to n of n choose k, k to the x k minus 1. This is true for any x real number. And you can get some interesting consequences if you take x equals you could take x equals 1, you can prove essentially that n times 2 to the n minus 1 is the summation of k equals 0 to n of n choose k times k. And yeah, that's similar to the formula that involves summing up all the binomial coefficients, but isn't, in some sense, it's equivalent. You can prove it. I'll show you in a second, similarly to that. But again, this is one way that this binomial formula can be used to deduce these identities. Here, again, like I mentioned, you can get a combinatorial proof of this result as follows. And maybe in this case, this is easier to remember. So let me write here combinatorial proof. So what I wrote above, you can consider that as an algebraic proof for this, let's say, identity here. And I mean, it does the job, but perhaps it doesn't give you so much insight of where in the world did you know, why would these two things be the same? So the combinatorial proof, it's a proof similar to the one that we did here, this proof here, where we essentially show that the expression on the left-hand side and the expression on the right-hand side, they count the same thing. And it's similar to this second proof that we did here, which kind of moved on here to show that, again, the two sides of our equality basically count the same thing. And to do that, we created a bijection between those two sets. So combinatorial proof is we look at these two expressions, the left-hand side n times 2 to the n minus 1 and the right-hand side, and we want to show that they count the same quantity. And so the trick here is to just come up with the right set. And so here's how it works here, and that comes through experience and solving more exercises. So let's consider the set of ordered pairs of the form, let's say, x and a. And x is an element of the set with n elements. A is a subset of it, subset of n. And x is an element of A. And we've seen something similar in the previous class when we had this identity involving n choose k and n minus 1 choose k minus 1. So here you want to count these order pairs. And let's count it two ways. So if you pick the x first, how many choices? So we have n choices for x. Now, so we have our set, let's say n, and we've picked x from here. Now we have to pick a. So once we picked x, a has to contain x. So a is going to be of the form b union x. And what is b? B is basically the leftover from a is a subset of the set n minus x. So b is a subset of a set with n minus 1 elements. Now it's clear that we're going to have as many a's as we're going to have as many b's. So the number of choices for a, they're going to be 2n minus 1 choices for a. So the cardinality of this set of order pairs, it's going to equal n times 2 to the n minus 1. Okay, so that's one formula. Now to get another formula is, let's pick a first. So if we choose a first, choose a first. Now we can choose a according to its cardinality. So let's assume that a has cardinality k. Then how many choices do we have for such an a? Well, it's going to be n choose k. And once we picked a, we have to pick x. And to choose x, x is an element from a, we have k choices. So it's going to give us k times n choose k. But This k can be anything from 0 to summation from k equals 0 to n, and so we get our result. Now, so let me give you, before we go to the multinomial formula, let me give you a few other things. So here's another problem that you can try. What is the sum of n choose k times k squared? So I won't give you the formula. So what does this expression equal? You can try to go from the algebraic proof. So try to find a closed formula, again, on the right-hand side. So try to find an algebraic way using binomial formula, and try to do a combinatorial way in which you count what we have here and is similar to what we did before, and see what the result you get. Now, there are other applications. Again, with binomial formula, you can, so this is 4, it's an exercise for you. Let me give you another way that you can apply it. And again, you start from this function, this identity with x plus 1 to the n is the summation from k equals 0 to n of n choose k x to the k. And now let's take a function, let's say g from 0, 1. I'll see in a second. You can do from other intervals if you want, where g of x equals x plus 1 to the n. Now what I can do is I can take a definite integral from 0, 1 of g of x dx. And what is this going to be? It's going to be an antiderivative of, well, we are graduate students, so we know what that is. X plus 1 to the n plus 1 divided by n plus 1 taken from 0 to 1. And that's going to be 2 to the n plus 1 minus 1 divided by n plus 1. So, okay. But at the same time, this expression is a definite integral from 0 to 1 of the summation from k equals 0 to n of n choose k x to the k dx. And what is this going to be? Well, it's going to be an antiderivative of the function inside. So that's going to be a sum from k equals 0 to n choose k x to the power k plus 1 divided by k plus 1 taken from 0 to 1. And when you calculate that expression, it's going to give us something like this, sum from k equals 0 to n of n choose k divided by 1 over k plus 1. So basically what we proved is this maybe strange looking identity, summation from k equals 0 to n choose k times 1 over k plus 1 equals 2 to the n plus 1 minus 1 n plus 1. So you can prove this identity in different ways, actually in another algebraic way, but this gives you a quick way, a neat way to get the identity. Let me give you another one. Okay. Now, what other applications can you get of the binomial formula? So we had 5, 6. Here's one which is quite important. Let's say we want to calculate n plus 1, some binomial coefficient, let's say choose k. Well, this one is going to be a summation. Let me put j here from 0 to k of m choose j times n choose k minus j. Okay. So here we have a binomial coefficient on the left, and we have a summation of this product of binomial coefficients on the right. So let me give you two proofs that are essentially equivalent. One is algebraic and one is combinatorial. So algebraic, we look at where could this n plus 1 choose k appear, and if we have this expansion of x plus 1 to the power m plus n, from the binomial formula, we know that this equals summation of k equals 0 to m plus n of m plus n. Well, let me use a different letter here. Summation of L from 0 to m plus n, m plus 1, m plus n choose L, x to the power L. So here we can say that the coefficient of x to the k in this sum in here is m plus n choose k. Very nice. But that coefficient, we can express it in a different way. We can write this x plus 1 to the power m plus n as x plus 1 to the m times x plus 1 to the n. And now we can expand each of them using the binomial formula. So it's going to be summation from I equals 0 to m of m choose I times x to the I. So that's one sum. And then we have the other sum, which is going to be summation from j equals 0 to n of n choose j x to the j. And now the question is, okay, how does x to the k, in this product, what is the coefficient of x to the k? Well, so to get an x to the k there, well, we have to pair one of these x to the i's with one of these x to the j such that their exponents add up to k. So let's say we pick an I from the left. So that's going to come with some coefficient m to the m choose I. And now if I want to get x to the k from in total, I need to pick an x to the k minus I from the right. And that forces its coefficients to be n choose k minus I. But now how large can I be? Well, this I cannot be bigger than k, so and can only be as small as 0. So it's going to be a summation from I equals 0 to k of this expression. So this is the coefficient, so we need to erase this part. And we get our answer. It's here, it's with I, above is with j, it's the same thing. So this is gonna be the proof that m plus n choose k equals this product. So this is sometimes called a convolution identity. And you can do quickly, let's do a combinatorial proof of this fact. So we'll put it here. So think about, it's very similar to the above proof. Think about a set with m elements here, m set here, and think about a set with n elements here, n set. And the number of k subsets of it, so we have this k fixed, you know that m plus n choose k is the number of k subsets here, and a k subset looks like this. So a k subset has some elements from the left side, and it has some elements from the right side. So if from this side we have j elements, then automatically from this other side you have to have k minus j elements. So basically what we're saying is m plus n choose k is the number of k subsets in this set. Let's call it A union B, where A is the m set and B is the n set. Okay, but I can count the number of these k subsets according to how much these k subsets overlap to the blue set, for example. So that's going to be a summation of j. Well, how big can the overlap be with the m set? Well, it can be as little as nothing, j equals 0. And how large can it be? Well, it can be as large as the whole k elements. And in how many ways can I pick these j elements here? That's m choose j. And in that, any choice of those j elements there can be paired up with any choice of k minus j elements here. So n choose k minus j. Okay. So that's again a nice and important formula to keep in mind. All right, so let me give you quickly, well, I guess one exercise before I tell you about multinomial formula. So here's something that you can try. How much is gonna be, let's say, summation from k equals 0 to m of -1 choose k, m choose k times m choose k. So try to figure out this expression. Okay. All right. So let's move on to the next page. I guess this is the 8. Now the binomial formula has a generalization which is called the multinomial formula. So here we have n and t natural numbers, and it's the same, similar to as before. So you have a sum that you raise to a power n, and you want to see how the expansion looks like. And now it's multinomial formula because we don't have just two terms in the sum. We could have more than that. So that's why t could be 2, 3, and so on. So if t equals 2, we get the binomial formula, but t could be 3 and so on. And the formula is as follows. You have this expression x1 plus x2 plus blah, 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 xt, and you raise it to the power n. Then you're going to have a summation, but how would the terms look like in the summation? What are you going to pick? So you're going to have x1 to some power, which we denote by e1, x2 to some power e2, xt to some power et. Clearly, because we have n brackets in total, n factors in total, all these exponents, they have to add up to n. And so the part here, it's pretty clear on the right-hand side. And now the question becomes, what's the number of choices? Like, in how many ways does this term appear on the right-hand side? And the answer is given by what is called a multinomial coefficient, which is this expression n choose e1, e2, et, which has a very easy to remember expression. It's n factorial divided by the product of the factorials of the elements at the bottom. So in the case that if when t is 2 and e1, then automatically e2 is going to be n minus e1, and this it's the same thing as the binomial coefficient that we know, e1 factorial times n minus e1 factorial when t equals 2. Now, how do you prove this this result? How do you prove that the coefficient is actually this expression here? So it's very similar to the proof of the binomial formula. So we have all these summation, these terms, x1 plus xt, x1 plus blah, blah, plus xt, x1 plus xt, and we have n of them, n factors. And now it's similar. So what do we want? We want to choose x1 from e1 brackets. So we have to choose e2 from e2 brackets, and xt from et brackets. These are some numbers. But because we have n factors in total, clearly we must have that e1 plus et has to equal n. Okay, so if we choose x1 from e1 brackets, the contribution from those x1s, when we multiply them together, it's going to be x1 to the power e1. So again, e1 could be 0, in which case we get a 1, which is okay. And then similarly, we get x2 times e2 to the power e2, xt to the power et. Okay. And now, how many ways can we pick x1? So the number of ways of, you have n brackets, and we have to pick e1 of them. So that number is going to be n choose e1. So that takes care of this one. Now, once we've picked the brackets for x1, those brackets are gone. You cannot pick anything else from there. How many brackets are left? There are n minus e1 brackets left. And from them, we choose x2, and we have to choose e2, such things. So we get this factor of n minus e1, choose e2. And it goes on like this until you get to xt. And actually at xt, you're going to have n minus the contributions from before, minus e1, minus e2, blah, 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 which it's all the numbers except et itself. So it's going to be actually et, and you choose et of them. So at the end, because of this formula, e1 plus et equals n, at the end, we just have, there's only one choice for xt, okay? Now, when we expand this, this product over here, what do we get? So let me erase here for a little bit. So when we write n e1 times n minus e1 e2, so here I have n minus e1 minus et minus 1 et, we get n factorial divided by e1 factorial divided by n minus e1 factorial. That's the first one. Then it's n minus e1 factorial divided by e2 factorial, n minus e1 minus e2 factorial. At the end, the last one is 1. And what's going to happen is that these factors, they're going to cancel out this way. So that one is gone. This one is going to be gone with the 1 over there, and so on. And so the result is going to be n factorial, e1 factorial, e2 factorial, et factorial. Okay, so that's the multinomial formula. Okay, all right. Let's see other applications of these binomial coefficients. So one involves the composition of a natural number. So a composition is a decomposition of the number, let's say, as an ordered tuple of natural numbers that sum up to n. So a composition of n is a decomposition, like I wrote here, this ordered k tuple, as an such that a1 plus ak equals equals n. So what is the number of compositions of, if I give you a natural number, what's the number of composition of them? So when n equals 1, we just have 1 equals 1. So you have, the answer is 1. When n equals 2, you can write 2 as 2 itself, and you can also write 2 as 1 plus 1. So the answer is 2. What happens when n equals 3? And so on. N equals 3, what do we have? You can write 3 as 3, or you can write 3 as 2 plus 1, or you can write 3 as 1 plus 2. So these are considered different because, again, as ordered pairs, they're different. This pair is 2, 1, and this pair is 1, 2. And then you can write 3 as 1 plus 1 plus 1. So we get 4. So there's some pattern that it's kind of clear, but maybe just in case things are, sometimes these patterns can be deceiving. Let's do one more. What about 4? 4 is 4. What about do 2 parts? You can do 3 plus 1. Let me write it like this. 1 plus 3, 2 plus 2. So I'll write equal. 3 plus 1, 1 plus 3, plus 2. What about 3 parts? 2 plus 1 plus 1, 1 plus 2 plus 2, 1 plus 1 plus 2. And what about with 4 parts? So in total, it looks like there are 8. Okay, so what we're gonna prove is the following. It looks like there is some pattern here. So we'll prove 2 things. Proposition 1, the number of compositions of n in k parts is n minus 1, choose k minus 1. And 2, the number of compositions of n is 2 to the n minus 1. Okay. So proof. So for the first one, so we'll use a bijective argument. If we have a composition, it means with k parts, we have this k tuple a1 plus ak, and n equals a1 plus ak. So again, a1, ak are natural numbers. And now what we can do is we can create a bijection between, let's create this function h from the set of all composition of k terms. So h is going to map a1 ak, is going to map it to a subset, to the following subset a1 plus a2, all the way a1 plus ak minus 1. So not the whole sum, but a1 plus ak minus 1, which I claim it's, so this is a k minus 1 subset of the set n minus 1. Now, it's clear that this is these elements are distinct because all of them are natural numbers. So if you start with a1 and you add a2, and then these two numbers are different and so on. So it's actually all these numbers, they go up. So let me write it here. a1 is going to be less than a1 plus a2, less than a1 plus ak minus 1. And now a1 is greater or equal to 1 because it's a natural number. How about this number? How large can it be? Well, this number is n minus ak, and ak is also a natural number, so this number is going to be at most n minus 1. And it turns out that this function, again, the key thing is that this function is a bijection. And I leave this as an exercise for you to prove. And because it's a bijection, it means that the number of compositions is going to be the same as a number of k minus 1 subsets of a set with n minus 1 elements. So you get this formula. And then for part 2, the answer is going to be, well, how big can k be? K can be as, or how small can it be? K can be as small as 1, can be as large as n. So you're going to be a summation of k minus 1 choose n minus 1 choose k minus 1, which is the sum from L equals 0 to n minus 1 of n minus 1 choose L, which is 2 to the n minus 1 by the binomial formula. All right, how are we doing on time here? Let me quickly do the weak compositions. So I'll just state the results and maybe we'll prove them next time. So the weak compositions, let me see how I get the pages. The pages are a bit messed up. This is 8. This is 9. 10. Okay. So weak compositions, the difference, change it here. The difference is that we have a 0 here. So you can go from all the way, as before, natural numbers, but 0 can appear there. So in this situation, k can be any number because you can just tag zeros to it. So how can you count this number of ordered tuples such that a1 plus blah blah plus ak equals n? And so the same questions as before. What's the number of weak composition, and what's the number of weak composition with k parts? So let's do first the number of weak composition with k parts. Let's put here with k parts. Okay. So, and can we actually can you use the things from before, the previous result? So here's how it works. So if we have a k tuple, let's say a weak composition of n. Well, so we know that a1 plus blah blah plus ak equals n. Now, can we do something to this k tuple and make it into a composition of maybe an unknown number? So the only thing that is different from weak composition to composition is that a1 could be 0. So how do you change the number a1 to make sure that they're not 0? You can just add up 1 to them. So let's define the sequence. Let's define b1 to be a1 plus 1. And let's define bk to be ak plus 1. So from this sequence of a1, ak, we just created a sequence b1, a k tuple b1, bk. And what's the deal here? Well, b1, bk are natural numbers because if a1 is 0, b1 is 1. So that's clear. And then what else do you know about b1, bk? If we sum them up, we're gonna get the same as a1 plus ak, plus we get a 1 for each term, so we get k terms, so we're gonna get n plus k. And it turns out again that this correspondence is a bijection, but it's a bijection between what? It's a bijection between weak compositions of n and compositions of one number of n plus k. But now that means that these two sets have to have the same cardinality, and we know that the number of compositions of n plus k is what? So from the previous formula, it was the number of composition with k terms is n plus k minus 1, choose k minus 1. So this is the answer here. If we look at number of weak composition with k parts, this is going to be n plus k minus 1, choose k minus 1.